Okay, so the first question, let's talk about quiz 3, and the first question says that a home pregnancy test cites the following. When the subjects using the test were women who collected and tested their own samples, the overall sensitivity was 75%. Okay, so let's write that down. 75% sensitivity. Okay? Specificity was low in the range from 52 to 75%. Okay, so it says from 52% to 75% for the specificity. Okay, suppose a subject has a negative test. So a test is negative. Okay, assume the lower bound for the specificity. So assume 52%. And what number is closest to the multiplier of the pre-test pregnancy odds to obtain the post-test pregnancy odds of pregnancy given the negative test result? And that is the DLR minus. So that's the negative diagnostic likelihood ratio. So that's exactly equal to 1 minus the sensitivity, 0.75, divided by the specificity, which is 0.52, which is equal to, well, let's just say about 0.48. Okay. What does this mean? Let's go through this again. So remember that the diagnostic likelihood ratios are probably best interpreted in terms of odds. So the odds of pregnancy given a negative test result equals the DLR minus times the odds of pregnancy in the absence of a test. So in this case, prior to taking the test, this person had some idea of what their chance was of being pregnant, and then now if they're sort of coherent with the probability calculations, their now calibrated odds of being pregnant is 0.48 times lower. So that's what the diagnostic likelihood ratio does for you. I should comment a little bit about kind of philosophies of thinking about these calculations, given given that they're kind of conceptually quite difficult, even though the math calculations are quite easy. So if you're thinking along the terms of a Bayesian, in other words, that this odds right here is a prior belief, this part is the evidence, the data, right? And then here's a posterior belief in the light of the evidence, then there's really kind of no quandary. Well, there's no quandary in either case. But let's suppose you don't think about these probabilities as being a Bayesian. Then what does the 0.48 mean? So presumably this person is either pregnant or not, so there's no sort of probability associated with it. Well, the way I like to think about it is this person is thinking along this line. So this person has a negative test result, and they're doing this probability calculation. So what they're then thinking is, well, among the collection of people who are like me, there's some percentage of them who are like me in the same circumstances as I am. So there's some percentage of them that are actually pregnant, and some percentage of them that are not, and that defines this odds right here. And so if we were to sample from that population and look at the percentage of them that had that were pregnant and their tests were negative, this probability would be 0.48 times lower. So the key idea actually is, if you want to think about these things in terms of a frequentist, right? These kinds of calculations as a frequentist, you can't think of it in terms of the one specific individual in a way that a Bayesian can. A Bayesian can just say, well, probability is my belief, it gets multiplied times the likelihood, and then I get a posterior. For a frequentist, you kind of have to think along the idea of conceptual populations, in which case this 0.48 is a contextual number. saying, well, if I was sort of randomly chosen out of a population of similar people who took this pregnancy test, my the percentage of such people drawn that had lower, that were not pregnant, would be 0.48 times lower than the percentage of people overall. And so you have to do those kinds of calculations, and it does seem a little bit confusing, especially in I think the frequentist sense. It sounds a little bit confusing, but on the other hand, I think intuitively we kind of know what's going on. But I think when you talk to statisticians, they make a lot of hay about these particular differences. But I think the calculations, regardless of what paradigm you're working under, frequentist, likelihood, Bayesian, whatever, the calculations still make sense, but you may have to think about the problem in a... Okay, so the next problem is a Bayes theorem problem. So I have here a picture of Thomas Bayes, so that for inspiration. Okay, there we go. So it's the same pregnancy test problem. Here we have the sensitivity is 0.75, the specificity is 0.52, and then the problem also stipulates suppose a subject has a negative test and that 30% of women taking pregnancy test are actually pregnant in the population being considered. What number is closest to the probability? We want the probability of being pregnant given that the test is negative. And so here we're giving that the prevalence of pregnancy among women taking this test is 0.3, 30%. Okay. So this guy right here, right, we can write this as the probability, using Bayes' rule, is the probability of negative given pregnancy times the probability of pregnancy, all over the probability of negative given pregnancy times the probability of pregnancy, plus the probability of negative given not being pregnant times the probability of not being pregnant. Okay, so this works out to negative given, so just to remind ourselves, the sensitivity is the probability of a positive test given that the person is pregnant. That's 0.75. The specificity is the probability of a negative test given that the person is not pregnant, so that's 0.52. So the probability of a negative test given that the person is pregnant is 0.25, and the probability of a positive test given that the person is not pregnant is 0.48. Okay, so now it's just a function of you have all the numbers here. You can plug all these into the equation right there, and you get that it's about 17%. Okay, the next question, quiz question 3, deals with the Poisson mass function. So, and the Poisson likelihood. So the Poisson mass function is mu to the x e to the negative mu all over x factorial. And so let's just calculate the MLE for a Poisson mass function. And I also noticed I misspelled Poisson poison on the quiz. So it's actually not a Poisson mass function. It's quite palatable actually as a mass function. It's not poisonous whatsoever. So at any rate, suppose that x1 up to xn are from the Poisson distribution with mean mu. Okay, then the likelihood associated with mu is equal to the product I equal 1 to n mu to the xi e to the negative mu all over xi factorial. Okay, so now this is mu to the summation xi e to negative n mu all over the product of xi factorial. So if we were to take the log likelihood, L, let's say, L of mu equal to the log, and whenever I write log, I always mean natural logarithm. The log likelihood of for the Poisson for the Poisson mass function, we have summation xi, I equals 1 to n, just to remind ourselves, times log mu, minus n mu. And then we have other stuff, but it doesn't matter as far as the likelihood is concerned because that part doesn't contain any parameters. So if we take the derivative of the log likelihood with respect to mu, right, we get summation xi over mu minus n. And if you set that equal to 0, that implies mu hat is equal to x bar, the average. Okay, good. And you can check a second derivative condition if you take the, you get negative summation xi over mu squared, which means that it looks like that. So this is indeed a maximum. Okay, so let's see, what did the question actually ask for? Oh, okay. So it just says you have an instance where you have three x's, x1 equals 5, x2 equals 4, and x3 equals 6. And it asks what's the MLE for mu. Well, it's just the average of these three numbers, which is, of course, 5, right? The average of 4, 5. Okay, so the next problem deals with a similar sort of thing as the last one, maximum likelihood, only this time it's the exponential density. So here we have x1 up to xn are exponential beta, which means, I'm saying in this case, that means that the associated density f of x for all the observations is 1 over beta e to the negative x over beta for x greater than 0. And you can verify to yourself that this is a proper density. And the question is, what's the MLE for beta? Okay, so let's go through it. So the likelihood for beta is, because we're assuming they're IID, the likelihood for beta is product I equal 1 to n 1 over beta e to the negative xi over beta, which is equal to beta to the negative n e to the negative summation xi over beta. Okay, and then the log likelihood associated with beta is log the likelihood associated with beta, which is negative n log beta minus summation xi over beta. Okay, so let's take a derivative of the log likelihood, L prime of beta, and we get negative n over beta plus summation xi over beta squared. We want to set that equal to 0, and that implies the solution that beta hat equals summation xi over n, which is x bar. Okay, so in this case, just like the last one, the MLE worked out to be the average, and you can double check that this is indeed the actual MLE. But you might be wondering, like, is there some broader principle as to why in all these cases the MLE is working out to be the average, when in fact the parameter is in fact the mean? You can check that beta is the mean of this distribution, just like mu was the mean of the Poisson distribution from the previous problem. And there is a more general principle going on here associated with so-called exponential families, and it's a little bit beyond the scope of the class, but there is some underlying principle that sort of densities that are of this sort of looking form here, where it's sort of something e to the negative something like that. They all have they all sort of follow a particular family, and that family then. Okay, so question 5 is a problem about geometric sampling. So we said the random variable x counts the number of trials until the first head from a biased coin with success probability p. The probability that x takes on a specific value is equal to p times 1 minus p to the x minus 1. And what's kind of interesting about this problem is that we kind of just know the answer, right? recall that the general likelihood principle says that it doesn't, the stopping rule doesn't, the stopping rule or the way you conduct the trial doesn't matter. In this case, we're going to flip the coin until we get the first head. So x can take on the value 1, 2, 3, and so on. And so the likelihood, so 1 if you flip a head on the first flip, 2 if you flip a head, your first head on the second coin flip, and 3, and so on. So x is the total number of coin flips, and regardless in this experiment, you're always only going to get one head. So you have a bunch of IID coin flips, and you want to talk about the success probability of the coin, p, and you have x trials, and you get one head. And so we know in advance that the MLE has to be the proportion of heads, 1 over x, which is really quite interesting that we can answer that without actually doing any work. But we could do the work, right? We could take the likelihood as a function of p is exactly equal to p times 1 minus p to the small x minus 1. So the log likelihood of p is equal to log p plus x minus 1 log 1 minus p, and then we could differentiate log prime is log likelihood prime with respect to p is 1 over p plus x minus 1 over 1 minus p. Oops, and then there should be a minus sign there. And equal, that should be a minus sign, equal to 0. Set that guy equal to 0. And what we get then is, let's see, so we get 1 minus p is equal to p times x minus 1, okay? And we want to solve that for p. So let's see, that is 1 equal to p plus p times x minus 1, and then if you continue to solve that for p hat, you get let me double check, you get 1 over x, just exactly like we knew had to happen, which is interesting, right? And the reason that works out that way is because this likelihood is exactly the same thing as a binomial likelihood, where we had 1 success and x minus 1 tails, 1 head and x minus 1 tails. And it's irrelevant that the sampling that occurred to get this according to the likelihood principle, and whether you do the arithmetic or just use the likelihood logic, then that is your answer.